Alright, so let's go over 4.2. So we learned before about all those other theorems, but now we're going to learn about the mean value theorem. And I actually have an interesting proof to show you that I've never seen before, and I came up with it on my own. So we have Rolle's theorem, and I really hate writing the conditions out, but Rolle's theorem states that f has to be a function that is const on closed interval AB, which just means that it includes the points A and B, differentiable on AB, and f of A has to equal f of B, such that there is a number C in that interval where f prime of C is equal to 0. That's pretty logical, so let's go over four ways that you can prove it to be so, or the only four cases that can possibly exist, which I'm not too sure how he proved it. So let's go over f of A and f of B. So the first case is between these 2 points. It's a straight line. Well, that's pretty simple. That means the function is constant, meaning that there are no input changes, and f prime of C has to equal 0 for all points within the function. Second case is this way. So we know that if f of x is continuous, then f prime of x has to, or we know that f has to be differentiable on the interval AB, which means that it is differentiable at every point on AB, meaning that it is continuous without that interval. And if it switches from a positive derivative to a negative derivative, and that change is continuous over that interval, well, the intermediate value theorem states that to go from negative to positive, it has to jump between 0. So that's how we know that there's an f prime of C is equal to 0. Same logic here. We have to go from negative to positive, or actually here it would be positive to negative, because it goes from positive rate of change and then negative rate of change. We go from negative 0 to positive. And the last case is a little bit difficult, or more intuitive. If it's a complex polynomial like this, we know that it still has to change signs between each thing, even if it oscillates, which means that there can actually be more critical points. So it does still prove the Rolle's theorem, except that f prime, there can be multiple c's in which f prime of c is equal to 0. So pretty intuitive proof right there, logical proof. So yeah. So what does the mean value theorem state? Now the mean value theorem states is a little bit different. F has to be const on AB, so the same exact conditions, except f of A does not have to be equal to f. Sorry, my handwriting is pretty bad, so let me do that. Then f prime of C is equal to the difference in points divided by, or just the slope between the points. So what does it state? 1 second here. Where C is between is in, so what does this state? So this means that there must be a point within that AB interval that the instantaneous rate of change is equal to the average rate of change. Physics students know what I'm talking about. And if you don't understand, we'll do it graphically. So notice that it's the same exact conditions, but except this time, we don't have the idea that f of A is equal to f of B. So I'm sure it still applies if f of A is equal to f of B, which it does using the Cauchy's mean value theorem. Let's just say that this looks like that. Well, if you were to draw the average rate of change, which essentially just measures delta y over delta x, as Leibniz would have pointed out, because Leibniz really liked the notations of infinitesimal changes. But notice I use delta y, not dy here. Then delta y over delta x is equal to m, or the slope difference here, which you learned in Algebra 2. Well, we know, Cauchy's, or not Cauchy's, Cauchy's mean value theorem states that for a slope here, if it's continuous and differentiable on that, if it's continuous on that open interval and differentiable or if it's continuous on that closed interval and differentiable on that open interval, there has to exist a slope within the line that will have the same exact slope. Now it states that at least there has to be one, but there can also be two, like we mentioned with the mean value theorem. So what are further applications of this? Well, cops actually use this to detect if you're speeding, because they can set up speedometers at that point and timers at that point, and if they do the difference between the velocities at the time, or not the velocities, if they do the difference between position at the time and divide it over the time, they can actually see that at one point you were speeding because you had to pass that instantaneous barrier. So, for example, you don't really have to worry about this. I just thought it was pretty interesting. Let's say that there's a car and there's a stop point 1 and stop point 2. If the speed limit is, let's say, 35 miles per hour, and at here you're at 0 miles, and here you're at here you're at 200 miles, or that probably wouldn't be accurate because you wouldn't be speeding all throughout. So let's say it's 200 meters and 0 meters, and let's say you pass this at a speed of 5 seconds, or 5 hours, let's say. And that means, let's just say that this is 200 meters per hour, which you don't really see that notation a lot. So 35 meters slash hour. All they have to do is do the difference between the 2 points divided by 5, which gives you 40 meters per hour. That means at some point you had to be traveling at 40 meters per hour, which means that they know you were speeding at one point. That's pretty logical as well because this is kind of the minimum speed you have to be going. But you can also be going for 30 meters throughout most of this ride and then speed up to like 200 miles per hour at the end of the ride. Or 200 meters per hour at the end of the ride. So Cauchy's mean value theorem applies there. So what is the proof? Well, I don't know how it's actually proved. I know they use Rolle's theorem, but I've seen algebraic proofs, and a lot of them are pretty hard to follow. But mine is quite intuitive, so let's look at mine. So again, remember that between this can be any graph, but between here we have a slope such that there's another graph or another point on the line that has the same instantaneous slope. Here it looks like there's about 3. So how do we prove this? Well, let's prove it with an even simpler graph, just to make it a little bit easier to follow. So we'll do a parabola here, and we'll draw this. Logically, you would assume this, that these two have the same line, but that's irrelevant to this proof right here. So what do we notice here? Well, we notice that f of a is not the same as f of b. So we can't say, wow, Rolle's theorem applies here. But I can use a more intuitive approach to this. And it's kind of the same way they do it in pre-calculus with polar conics sections. But I'm going to do it differently. So is there a way we can orient this graph such that the heights are equal to each other? Oh yeah, that's pretty simple. I'm going to just take this and I'm going to rotate it a little bit. And let's rotate it a little bit to the left. So we're going to get that graph. And we're going to probably get something like f of a and f of b. And now we get this point. So all we did was we truncated each value down by a certain point. What does this look like? Well, this looks like f of a and f of b are really similar to each other, such that there has to exist f prime of c is equal to 0. So if f of b minus f of a divided by b minus a is equal to 0, or is equal to f prime of c, what does that prove? Well, that's exactly what the mean value theorem states. So essentially, the difference between these points divided by the interval of these points is equal to the instantaneous rate of change. That's quite interesting. And my proof is, I've never seen it before, but I'm sure someone has done it previously in the past, because calculus has been around for hundreds of years. But here you can see that if you just orient the graph, you can use Rolle's theorem to prove the idea, which is why I believe that they have the same restrictions, such that f of a and f of b have to be equal, or that they have to be continuous and differentiable on that interval. So yeah, that's the simple proof there. And that's super logical here. So, now I'm going to do, I guess, another theorem here. I'm going off my notes here, so I'm trying to remember all the theorems that we have. If f prime of x is equal to 0 for all x in interval AB, then f is constant. Well, that is really super logical to assume. I mean, if it's not change, so if f prime of x is equal to 0 for all points, that just means it's not moving at any point during the interval. If you put it into plain English, if f prime of x is equal to 0 for all x in an interval, that's just saying if something is not moving for all of the points within an interval, then it's not moving. It's constant, which is like logical. So I guess you don't even need